And welcome to Acoustics Derivations. In this video, we will be talking about a few miscellaneous topics that, while important, are not large enough of a topic or a point to dedicate a whole video to. So the first thing we're going to talk about is sound levels. Now, sound levels are expressed in decibels, dB, and the most common and the one you're probably most familiar with is a sound pressure level. And the equation for that, SPL, sound pressure level, is 20 log base 10 of PRMS over P ref. Okay, so PRMS is your root mean squared pressure of your particular waveform, and P ref is either P ref is either 20 times 10 to the negative 6 pascals for air, or 20 micropascals, and 1 times 10 to the negative 6 pascals for water. This means, because the reference pressure is different, that, for example, 80 dB in air does not equal 80 dB in water. So often you'll see sound pressure level reported as, for example, 80 dB re 20 micropascals. So what that means is 80 dB relative to 20 micropascals. And so that will be for air. Next, we have intensity level, the level. Once again, expressed as a dB, we have intensity level is equal to 10 log base 10 of I over I ref, where I ref, once again, the reference, so this is the reference intensity, is 10 to the negative 12th watts per meters squared in, so this is in air. I'm not sure what it is, water, but so this is in air. Finally, we have sound power level. Sound power level. And not to get confused with SPL, I will denote this PWL, so just power level. And this is 10 log 10 of your power, W, over your reference power. And your reference power is given by 10 to the negative 12th watts. So the next item, so this summarizes sound levels. Just a quick examination. There are, of course, more detailed discussions in the literature, and, for example, how to deal with finding the sound pressure level of multiple sound sources at once. But I'm just listing out the general expressions for these particular levels. Next, we will talk about the Helmholtz equation, a very, very important equation in acoustics that is used kind of as the starting point for a lot of different derivations. So we begin with the wave equation. We have the wave equation here. The wave equation in terms of pressure, that is. And we then let the pressure, which is a function of position and time, be equal to some magnitude, P, it's going to be complex or real, times e to the j omega t. So now we're going to take P, little p, and plug it into the wave equation with our new expression. We have the Laplacian of capital P, and we know that e to the j omega t does not depend on position. And this is going to be equal to We're going to take two time derivatives of e to the j omega t, and let me write that on this side because it's not gone, but we have e to the j omega t. In fact, let me put that out front so it's a little bit more clear. So e to the j omega t, and then times the Laplacian of p. And we're going to take two time derivatives of e to the j omega t, which is going to give us negative omega squared, because the j's multiplied together give us a negative 1. That's over c squared. And then we're just left with p e to the j omega t. First, we cancel the e to the j omega t's on both sides, and then we let k be equal to omega over c naught, and this is the wave number. We plug that in and move everything to the left-hand side, or the right-hand side, I suppose. But we'll do the left-hand side and obtain what is known as the Helmholtz equation. So the Laplacian of p plus k squared p is equal to 0. So what's helpful with this is the time dependence is now gone. This is purely spatially dependent, this equation, because there's a Laplacian, but there's no time derivative. And we've actually taken out the e to the j omega t. So like I said, this is a very, very useful starting place when deriving some specific derivation. Finally, let's talk about velocity potential. So velocity potential is given as, so we have velocity u is equal to the gradient of phi, where phi is the velocity potential. So this is just a definition. U is equal to grad phi. The velocity potential, sometimes in literature, you will see velocity potential instead of velocity or instead of pressure in specific equations such as the wave equation. So that clearly means there's a relationship between velocity potential, and pressure. Well, we see the relationship between velocity and velocity potential here, but what is the relationship with pressure? So let's look at the linearized momentum. This is the left-hand side of the linearized momentum equation. And if you recall, this is equal to negative grad p. But before we do that, let's plug in velocity potential. So we'll have not grad d phi dt. And then once again, this is equal to negative grad p. If we integrate over the volume, to eliminate the gradient, we obtain p is equal to negative rho naught d phi dt, which could equal negative j omega rho naught phi if phi is a time harmonic function whose time dependence can be described as e to the j omega. So this is the relationship between u, phi, and p in terms of velocity potential. I mentioned that you can have a wave equation in terms of velocity potential. I'll challenge you to show this yourself using this relation, but you can find that the wave equation is simply given as the following. And we recognize that looks exactly like the wave equation because it is a wave equation, but with phi instead of p or instead of u. So that concludes this video on a couple quick topics that I wanted to discuss, but that weren't long enough to make it into their own video. So velocity, potential, the Helmholtz equation, and sound levels. Thank you.